So you got in your e-Golf and got greeted by the message, error, electrical system, stop. I'll try and keep this short to start with, but then I might ramble on about details afterwards if anyone's interested. This is probably the reason your car won't go. What is it? It is a resistive heater. It's what heats your cabin up. Why does that stop the whole car working? That'll be in the details later. Take it to Volkswagen. They will quote you just shy of £2,000 to replace this, including the part and labour. You can probably pick one up for about £100 used off of eBay, and it's straightforward to fix. Caveat, you should be experienced with EV electrical systems. I'm not going to recommend you try this if you have no clue about that, but you might be able to tell someone else is experienced what needs doing if they're greeted by a whole load of diagnostics codes they don't really understand. So that was a summary. So a bit more detail. This came out of a 69 plate 2020 model e-Golf. Chances are it's very similar or the same in various other vehicles, maybe the e-Up, maybe the Seat equivalent. I can't be sure. So from a diagnostics perspective, VCDS was able to tell us a whole load of errors, including that there was a fault with the HVAC, or high voltage like air conditioning or climate control system, of which this is kind of a part. But the interface we had was not really compatible with the vehicle, so it was not a very good set of diagnostic details. AA's system they use is a Bosch one, and that just came up with one fault, which said pre-charge timeout, which actually, although I'll get into the details later, is a very accurate description of why the car wouldn't go, although it doesn't really help diagnose the exact thing that's failed in the vehicle. Well, you could say that, but you could also say that as there's only a small number of things wired up to the high voltage part of the vehicle, that does kind of narrow it down quite a lot. So this is one of those things. This orange connector is a high voltage connection. The problem is that this thing has failed on. Again, I'll come back to details later as to why that is a problem. Now, obviously, if you buy one of these off of eBay, it's been used, it may not work. That's your call if you want to take that risk, depending what position you're in, whether you've literally just had this fault or whether you've already been towed to VW. There may be other charges. VW will charge you a nearly £300 just to run diagnostics before they do any other fixing. That would be included, I think, in that nearly £2,000 if you were to go ahead with the repair. You've got to take into account charges for being towed. If it doesn't work out and you then have to tow it back, then obviously that all adds up. So short of it is, you might get away with just using a second-hand one and getting it going for not much more than the cost of the part, depending on who installs it. But yeah, it's up to you to make that decision. So I mentioned this heats your cabin. It's not immediately obvious to some people how that happens, looking at it. So it's a bit like central heating system. This is your boiler, but it's electric. Fluid runs through this. The fluid runs through a heat exchanger in your cabin. A fan blows air through the heat exchanger that heats your cabin up. It's powered from the high voltage battery connected to here. This is, I imagine, permanently live all the while the car is energized or on, as in you're driving. And only ever not live when the battery isolator is engaged, isolating the battery, so as in when it's parked and not being used. I imagine this is even live when you plug the charger in, because that would engage the isolator in the battery. So that's the power. This one here is another connector. This is a control connector, so this is probably there's probably a whole little computer in here, microcontroller, and this is going to be CAN bus or something similar, instructing the innards of this what to do in terms of switching the heating elements, if there's multiple ones of them, on and off, and potentially controlling the amount of power going into those heating elements. Yeah, so this is all a bit of speculation, links I've not looked in here yet, but that's what I'm about to do. I'm going to open it up and see if we can actually see what's in there, whether anything looks serviceable. Okay, so you've isolated this part in your vehicle. How can you confirm that this is actually the fault before you shell out for a replacement? Well, that's quite simple. If you use a multimeter set to your ohms or resistance reading, and you run it across these two metal pins in here, so one probe on this one probe on this one, you should see on a working unit that's got open circuit, it was actually about 1.4 mega ohms in one direction. If you change polarity, the meter couldn't measure anything. Open circuit. If, like this one, it's failed on to some extent, you're going to see a fairly low resistance across here. In this case, it's about 90 ohms, which is equivalent to about 1.5 kilowatts. This thing actually says somewhere on it that it's a 5 kilowatt heater. There we go, 5 kilowatt, 350 volt. I imagine there's more than one heating element in here, so that it can switch between different number of heating elements to provide a different amount of power. I had originally assumed there would just be one and it would like use pulse modulation, but maybe it's not that. Maybe it has got separate heating elements. Because if it had failed fully on, a 5 kilowatt heater would be significantly lower than 90 ohms. Anyway, so that's your quick test to see if this unit is broken in your car and needs replacing. So something I've noticed is that this is listed as a PTC, or positive temperature coefficient heater, in various places, and yet when it was cold, when it first came out of the vehicle, I measured about 90 ohms across the power terminals. Once it warmed up a bit coming inside and I started to make this video, I measured about 86 ohms. Not a massive difference, but that feels like an NTC rather than a PTC heater to me, so something to explore. Next up, I'm going to attempt to diagnose what's actually failed in here to see if it's actually repairable. I'm going to assume that there's either a relay, I suspect not a relay in this case, probably some kind of FETs, maybe a silicon carbide or other FET or set of FETs, one of which has failed short circuit, which is a common failure mode for these particular parts. Whether I will actually be able to get to anything in here remains to be seen. It may well be potted, like full of silicon or some kind of resin, which makes it pretty much impossible to work on. We will find out. Right, so here we go, opening up. Some of these screws are different lengths. Oh, that cover doesn't just pull off. See straight away there is what's got green. I like to see stuff that really green possible. No? Okay, it's cover off. So what I'm here, I believe I have multiple components, so why we can come through. might be FETs. I think we've got 3 FETs under here possibly. TP out. We've got a connector there to take off. So here's the PCB removed from the heater. So this controls the heater, has a permanent power supply comes in here. We've got a negative or 0 volt or ground, whatever you want to call it. Runs round basically as far as here. This is a current sense. So all the actual ground, everything on the board that wants ground is reference to the other side of this current sense IC. The positive comes into here and it goes straight into one of the pins of the heater. It also goes over to here. This is the same over here to another pin of the heater. So there's one heater element between these 2 contacts here, and there's 2 more heating elements. This is a common tied permanently to the positive, and then there's 2 negatives here. We've got 3 control devices, they're IGBTs. This one, and this one. They're actually pretty much identical as far as I can tell from the data sheet. The only difference is this one has a bigger surface area for sort of allowing the heat to be removed from the little silicon chip in there onto the heatsink. So this heater actually has a lower resistance than these 2. In fact, I will confirm this in a bit, but I'm suspecting that this one is half of one of these and one of these is half of the other one of these, such that we get a 3-bit binary, or basically a 3-bit digital heater, so that we've got sort of 0 to 7 range of power levels for this heater. So this is the overall board. We're interested in these. I'll just give a quick overview of what some of the other bits are. I've already mentioned we've got a current sense thing. I can't remember if I mentioned this is a LIN interface. It's only got 3 pins, so it's not CAN bus, it's LIN bus. It's kind of does a similar thing to CAN bus, you can say, as in it allows computer chips to talk to each other, but this one is simpler, more cost effective. It does it with a single wire plus the power wires, so there's going to be a ground, the LIN bus, and probably a 5-volt signal in this 3-pin connector. This is the microcontroller, integrated flash, so there is a program or software flashed into this chip that allows it to do what it needs to do. These are probably A to D converters, but they're an unknown part. There's no documentation for these whatsoever available online. This is quite common throughout electronics industry, that manufacturers that make large enough volumes can get companies to custom make like chips for them, a run of chips. So this says it's clearly analog devices. It says ADW. What does it say on it? Can't remember. It says ADW80028 ARWZ. But as I say, you won't find anything online as to what that is. So we are interested in these 3 FETs. One of them is fried. I've already determined this. So these are IGBTs. They're kind of a hybrid of a FET and a bipolar transistor. The reason for that, the reason these will have been chosen will be a combination of design parameters and cost, or bill of material cost, because being a 350 to 400 voltage battery, it's fairly high voltage. To run a 5 kilowatt heater, you've also got fairly high current. So you end up needing silicon that can cope with those voltages and currents simultaneously. There are things like silicon carbide and GaN that will do that, but at a great cost. These don't need to be switching at high speed, they're just on or off basically. So these are a sign of compromise. So they're relatively low cost, but able to handle the power levels that we need. So this is the control or gate pin when this has got a voltage on. So these are voltage controlled switching devices, not current controlled. If it was a bipolar transistor, it'd be current controlled. A small current in here is magnified and a large current will flow between these two. This is voltage controlled like a MOSFET. So when there's a voltage on here, a current will flow between these. So what we should see is that these 2 pins are open circuit when there's no voltage on there. And if we do that on this one, there is no continuity, it's open circuit. Same with this one. However, this one is shorted, and that is the reason that your car with this volt won't move. Again, I will come back to it in a little while, why the whole car won't move because of that, rather than just the heater being on. But this chip, or this IGBT, which you can obtain for about £15, possibly plus a handling fee, is basically the whole reason your car won't move and why you'll be paying VW £2,000 to have it fixed if you go that route. Why has it failed? I don't think it's been over voltage, because this is rated at 1200 volts and the maximum battery voltage will not be more than 400 volts. There is a chance that there's ringing when it switches and that there's then spikes that go outside of those boundaries, but I imagine this has been designed with that in mind, and that the 1200 volt rating this is well above any associated ringing. It will not be getting overloaded with too much current because it's a 5 kilowatt heater. These things are rated for 81 amps. So the last thing is those specs are only sort of correct, or you can only use them within those parameters if you can take the amount of heat. These things dissipate heat. They have a sort of integral resistance, so when you've got current flowing, they get hot. That's partly what this is, and it's partly what the bulk of the heater is, which you may notice is missing from my desk in a minute. There's a reason for that will become clear shortly. But these are intended to be clamped to the metalwork in the heater with the fluid running through it to take some of the heat away. Now what I noticed is, looking at this, I don't know if it will show up on the camera, but at a certain angle you can see the mark that these two have left imprinted on this. There is very little of anything in the way of a corresponding mark for this one. And again, if you look on the actual thing itself, you can see these two are kind of got this grey glazed effect on them, where this has been pressed on them the whole time, whereas this one has only got this little area here, most of it's shiny. Now, for this to effectively be removing all the heat from this device, this thing needs to be well in contact with the thing that's taking the heat away, as in the rest of the metal block. I think in combination with, where's it gone? There was a plastic clamp that holds this against the rest of the body, which I took off very early on. Right then, back from the short pause. What I was trying to find was this. This has little rubber feet on it, little rubber cushiony things. Push through these holes, screw down, and clamp these against the, oh, that's cold. Clamp against these blocks in here. So these help take the heat away from these switching devices so that they do not overheat. One of my theories is that these legs on here are actually so thick and tough that this little rubber thing has not been able to push this against there hard enough between there, hence why it hasn't left an imprint on here like the other two have, to actually keep this thing cool. So this thing has got too hot and failed. Okay, a bit more about this part of it. You might notice it's looking a little bit frosty in there. There's a reason for that. It's been in the freezer. Why has it been in the freezer, you ask? It's been in the freezer because this isn't just any old set of heating elements. It's not just pieces of wire in here. This is a PTC heater, positive temperature coefficient. That means that as it heats up, its resistance also increases, and thus the amount of current that flows through it decreases. And what that allows it to do is sort of find an equilibrium, so it won't overheat. It doesn't need a thermostat because it self-regulates the temperature. So I'm going to measure the resistance of these because I suspect that one of them is more powerful than the other two, and of those other two, again, one of them is more powerful. And that's partly the reason why one of the FETs is larger than the other two. What it would also allow you to do, if they're scaled correctly, is give you effectively 8 different temperature ranges, 8 different power levels if you include off as one of those power levels, so 0 to 7. So we have got, out of these contacts, the board goes on that way around. This one says TP in. I think that's a temperature sensor for the input port up here, so the temperature of the fluid when it's coming in. And we've got TP out over here. These two, temperature sensor for the temperature that leaves the thing. We've then got, I think this is the primary, most powerful heating element because it's on the largest device, and I've already seen that the spec of these is otherwise the same. The difference is this one can dissipate, this one can allow more heat to be transferred out because it's a larger surface area. And so with this cold at minus 18 degrees straight out the freezer, this should have the lowest resistance, and that's going to be the highest, correspond to the highest power possible for this heater. And it's supposed to be a 5 kilowatt heater. We have currently got, saying 140 ohms, which is interesting because I read it to say 90 earlier when it was warmer. And then over here, 410. I know this one is the common, and that these two each feed back to that one because of the way the circuit is wired on here. The power, positive power in, is coming straight over to this pin, which is this top one here. And then one of these switches, this one, switches this heating element, and then this one the other heating element. So that's why I'm measuring between here, and I'm seeing 410 ohms, this one, 290 ohms, this one kind of 136.7 ohms. I put that back on there. Yeah, 137 ohms. So for some reason the resistance of this heater has gone up at the minute, not down. I wonder if there's kind of a bit of a dip in the curve at some point, so where it's actually gone up when it's that cold, and that as the temperature rises it's actually going to go down and then start to go up again, because at the minute that doesn't make much sense unless there is something further wrong with this unit. I've now flushed it through with hot, not really hot water, but fairly hot water. and we've got 70 ohms, 146 ohms, and 174 ohms. This is looking very much like an NTC, not a PTC heater at the minute. Let's go even hotter. Okay, let's add water that's not far off boiling in it now. 55 ohms. 113 ohms. 140 ohms. This is looking very much like an NTC, not a PTC heater. So I think I'm just not able to get this thing hot enough to get to the point where the PTC effect kicks in, and that I'm just seeing it dropping because there is basically a curve to the temperature versus resistance, and it may go down a bit before it starts to come back up, and at some point when it gets to a predefined switching point, the resistance should just suddenly go up, and that's the point where it will start to regulate the temperature. Without another one to compare, which I know is working, I can't really say anything more about that. So conclusion at the moment is this has failed, potentially because it doesn't have good enough thermal management, in that it doesn't make good contact with this on here. I may try replacing this and try testing that theory. Right, final comment. Question from earlier. Why does this £15 part failing render your entire car inoperable? Well, that has to do with a combination of factors. We're operating at high-ish voltages with very low resistance batteries to be able to deliver a very high current to drive a motor which can propel a vehicle along a road. That's in combination with inverters and other electrical things like the DC to DC converter that charges the 12-volt battery, and the AC to DC converter for charging the car. These all have capacitors in. Now the battery also has an isolator in it, which disconnects the battery from the rest of the vehicle when it's not being used. That's for safety reasons and for longevity reasons, both to stop the batteries being discharged slowly due to leakage, to stop capacitors being constantly have a voltage on them, which will make them last less time. Now, you can't just directly connect a 350 volt battery with hundreds of amps, thousands of amps of power current available to a set of empty capacitors, because you are effectively shorting the battery. At that instant, when you make that connection, the capacitors are 0 volt, you've effectively made a short circuit and a fireworks display. So to allow the isolator contacts to be closed, you need to first of all reduce the voltage across the isolator contacts by relatively slowly charging those capacitors. So a small current, so there's two switches in the battery. There's the main one which closes once the capacitors have been charged up. There's a much smaller one that closes, which allows a small regulated amount of current to flow to charge those capacitors up. Now, to stop that burning out, due to a fault such as this one, there is then a timeout imposed on how long that should take. If it takes too long, you get the error code you're seeing. The car, well, you get the error we were seeing on diagnostics, pre-charge timeout, or pre-charge took too long. Those capacitors are taking longer to charge than is expected. The system decides that there is a fault, and it's exactly right. This thing being shorted on, this heating element trying to load that small switch, the small switch is designed to let a few amps through, not the amount of current that this thing's going to draw. Probably less than a few amps. It might be less than an amp. With this thing providing a load, those capacitors, instead of charging up at a rapid rate like that on a curve, they're sort of gradually charging and probably only getting to about there. Then that timeout kicks in, and that's a fatal error. The battery isolator cannot close its contacts. If the battery isolator cannot close its contacts, your car cannot move along the road. And that is basically the reason why this heater being failed doesn't just make your cabin hot, it stops the car working altogether.